Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to continue our discussion of HDL bits problem solving. And in our previous video, in the part 1, we have already discussed a few problems and I haven't saved or haven't created the account, so I cannot see any progress. So better when you are working with HDL bits, I recommend you to create an account so that you can have a track of what problems you are going through. So if you haven't watched the previous video, you can just watch it out in our channel. And if you don't know anything about Verilog, I recommend you to once go through this particular playlist, which is already available on our channel, where you can basically able to get understanding of all the particular things about this Verilog, right? Yeah. And this is what I was talking about. This is a part 1 video which we have discussed. Now let's start with part 2 of this particular session, right? Now, without any further delay, so we are going to start with this particular replication operator. In our previous video, we have discussed about to vector reversal. Now, let's discuss with replication operator. So let me open this. Yes. So we have this replication operator. About this replication operator and all, we have discussed in great detail in our playlist videos. If you don't know about this replication operator, I recommend you to once go through this particular playlist where we have discussed about everything about this replication operator and all. Yes. So coming, or else you can read from here the theory part and all. So let's see what is the problem statement we are going to have. So build a circuit. Yes. So in this question, build a circuit that sign extends 8-bit number to 32-bit number. This requires a concatenation of 24 copies of the sign bit, that is replicate bit 7 24 number of times, followed by the 8-bit number itself. So this is a problem statement which we are going to have. So let us write down this assign out, which is equal to, I need to have a concatenation operator present. Now in this I'm going to replicate the MSB for 24 number of times. In of 7 is what I need to replicate for 24 number of times, and followed by the remaining number, which is in of 6, sorry, the remaining number 7 down to 0. So this is what we are going to have, and let me submit and let us run it. Some syntax error. So we have opened the curly braces. Okay, sorry. Here we need to have a square bracket and the curly braces. Yeah, just a small error. Let's check it out. Yes. So status is success. So let's see the model sim Portus prime results messages. These are all the messages. Given 5 1-bit signals A, B, C, D, and E, compute all 25 pairwise 1-bit comparisons in the 25-bit output vector. The output should be 1 if 2 bits being compared are equal. For example, out of 24, that is 24 bit will be equal to not of A XOR with A. That means A is equal to A. So out of 24 is always 1. Okay, so basically they are asking us to compare this to, and we need to update that particular variable. So this is what we need to do. Again, I'm reading the question again. So given 5 1-bit signals A, B, C, D, and E, compute all 25 pairwise 1-bit comparisons in 25-bit output vector. The output should be 1 if 2 bits compared are equal. So if the 2 bits are equal, then we are going to update this vector as 1, or else this vector will be equal to 0, and we are going to perform this combinational operation, which is not of A XOR with A, right? And out of 23, which will be equal to not of A XOR with B, and so on. Okay, and we are going to perform this XNOR operations between all these particular things, and we are going to update in my out. So as the diagram shows, this can be done more easily using replication and concatenation operator. So the top vector is a concatenation of 5 repeats of each input, and the bottom vector is 5 repeats of concatenation of 5 inputs. Okay, so we need to write down this thing. So basically we need to concatenate the things. That's it. They are asking to concatenate the upper inputs, upper vector as well as the lower vector they are asking us. So let us update this one. Let me uncomment this particular line. So assign out is equal to, so first one will be 5 times I need to replicate my A. So I can see 1, 2, 3, 4, 5 times I need to replicate my A. So I'm going to write it down 5 times I need to replicate my A, and 5 times I need to replicate my B. Sorry, I need to use curly braces over here. Yeah, 5 times I need to replicate my A, and 5 times I need to replicate my B, and 5 times I need to replicate my C, and 5 times D, and 5 times E, right? Yes. So this is what we are supposed to do. So 5 times A, 5 times B, 5 times C, so that we are basically going to form this vector, and we need to get A, B, C, D, A, B, C, D, A, B, C, D. Okay. So let's do one thing. Let me declare one more small register of 5 bits, let's say 10, and which is equal to concatenation of A, B, C, D, and E. And I'm going to replicate temp for 5 times. So 5 times of temp, 5 times of temp, 5 times of temp. Let me copy this. So 1, 2, 3, 4, and we need to have it for 5 number of times. So let me give it one more time. Yes. So this is what we have done. I've replicated 5 for 5, A for 5 number of times, B, C, D, and E, and temp for this many number of times. Okay, so let's see whether it is working or not. Let me submit it and let's check it out. No, temp it's showing. Okay, okay, we cannot have temp directly over here. Okay, let me declare it as wire, and so that I can assign it. So assign temp is equal to, yeah. Now let's check it out. I think now it should work. So this is how we are basically going to, yeah, we are getting success messages. So we have entered into the concept of modules, right? So this theory and all, I'm not going to read it out. We have already covered in our playlist. If you want, you can once check it out, this playlist. Let me scroll down. So connecting signals to modules and all, we have discussed about port connections and all. Yeah, you can check it out over in this particular playlist. And port connection by name and port connection by position, and yeah. So above line instantiates a module, instance to the name. Notice the ordering, okay, fine. Regardless of position, also notice, okay, expected solution around one line. What we need to do, module top underscore module, input A, input B, output out, okay. What is the question where it is given? Okay, so connecting signals to a module ports remain connected. This is syntax is more verbose. Okay, okay. So this is the diagram we need to implement or we need to instantiate. They have given already the top module. So in this particular code, they have already written module top underscore module input A, input B, output out. Okay, fine. And we need to instantiate mod underscore A over here. Okay, let's instantiate it. So mod underscore A, let's say DUT is nothing but design underscore test. And I need to instantiate A, B. I'm following connection by order, port connection by order. So I'm going to write down simply A comma B comma out. A comma B comma out, right? Yes. Let me submit it. Yes. So it's getting success. Yeah. So let's move forward. It's a simpler one only. So module positions. This problem is similar to the previous one. You are given a module name mod underscore A that has two outputs and four inputs in that order. You must connect six ports by position to your top level module out 1, out 2, A, B, C, D, and D in order. You are given the following module. So this module is already given and the order is different. Output, output, input, input, input. Okay. So we need to connect them accordingly, right? So we have given a top module and we need to instantiate our mod underscore A accordingly. Okay, fine. So you must connect the six ports by position to your top module's port, out one, out two. First is out one, next is out. Okay, let us write it down over here. So in this particular code, so my design name is mod underscore A, DUT, and first I need to connect the outputs which is being given in the problem statement. So out one, out two. Next is A B C D. Next is A B C D, and let me submit it. Let's check it out. So if you have watched all this particular recordings, it will be very easier to solve this particular problem statements. It is very simple. Okay. So yeah, this is it's getting success. Yes, let's move forward and let's go to module name. So the problem is similar to module. You are given a module named mod underscore A that has two outputs and four inputs. So this mod underscore A has two outputs, out one, out two, and four inputs, IN1, IN2, IN3, IN4. And in some order, you must connect six ports by name to your top level modules. So put in mod underscore A, port in top underscore model, output out one to out one, output out two, out two. Okay. So we need to basically connect them by using connection by name. That's it. So okay, so let's connect it. So mod underscore A DUT, and I need to basically follow connection by name. This is what I need to follow. So since I'm going to follow connection by name, order is not an important. Okay, but let's follow whatever the thing they have asked for. So mod underscore A signals are okay, out one. Okay. So out one, out two, in1, and the syntax is you should have dot present, dot, dot, and dot in2, and dot in3, and dot in. Okay, so this mod has in1, in2, in3, in4. So these are the signals, and I'm going to write down over here out one and out two, and here I'm going to write down E. These are the signals which are which or of top module signals A, B, C, and D. Yes, so let me run this, submit it. Just I'm connecting them using connection by name. That's it. There is no much more in that. Yes. Okay. Just I'm following connection by name. Previously, I was using connection by order. Now I'm going to follow connection by name. So let me once try to change the order. Whether let's see this particular simulator is accepting or not. Comma dot, here also dot, we should write it down, dot. Okay, let me submit it. Okay, yeah, it's not basically giving you any kind of errors and something, right? Yeah. So in connection by name you can follow any order, it's not an issue. So let's move forward with the next question, module shift. So you are given a module my underscore DFF with two inputs and one output. So my underscore DFF is a module with two inputs, which is clock and D, and one output, which is Q. And instantiate three of them, then chain them together to make a shift register of length 3. The clock port needs to be connected to all the instances. So basically we need to create this particular model and we need to replicate it or create the instances of this model for 3 number of times, and clock should be given to all the models, right? The model provided to you is model my underscore dff. That is, this particular model is provided to us. And know that make the internal connections, you will need to declare some wires. Be careful about naming your wires and model instances. So using wires, we need to connect these three modules inside the top module. That is our requirement. So yeah, fine, let's do it. So already my underscore dff is given to us. Okay, so no need to worry about it. The code of my underscore dff is already written. So let us instantiate them. My underscore dff dut1. I'm going to follow connection by order. My underscore dff dut2 and my underscore dff dut3. Yes. And for connecting these two modules, I'm going to use a wire. Obviously, we need a wire for connecting the modules. W1. Let's say this wire is W1. And for connecting these two modules, I'm going to use W2. So wire W1 and W2. Now let us follow the order. So order is my underscore dff is having the first signal as clock. So I'm going to give clock as one of the input, and D is another input, and Q is the output. So output, I'm going to connect it to the wire. So you can see the output of my underscore dff is given to the W. And next is clock is common. And the second flip-flop input is given from the first flip-flop output. So I'm going to take the wire, which is being given from the first flip-flop, and the output is given to the second flip-flop wire. Next clock, input is W2, and output, you can see it is given to Q. Okay. Yes. So this is connection by order, which I'm following, and it's a simple 3-bit shift register. Okay. So this is how I'm going to connect. And let me run this, click on submit, and let's see. Yes. So status is success. We have the all the test cases which are running perfectly. Mismatch is equal to 0. Yes. Okay. So let's move forward and let's say shift 8. I think it's a 8-bit shift register. So this exercise is an extension of module shift. Instead of module ports being only single pins, we now have modules with vectors as ports, to which you will attach wire vectors instead of plain wires. Like everywhere in Verilog, the vector length of the port does not have to match the wire containing to it, but it will cause zero padding or truncation of the vectors. This also we have discussed in great detail in our playlist. You can once watch it, what is this theory is basically telling us and all. So we will move forward, and we are given with a module DFF8 with two inputs and one output that implements a set of 8 D flip-flops. Instantiate 3 of them, then chain them together to make 8-bit width, 8-bit wide shift register of length 3. In addition, create 4 cross 1 mux not provided that chooses what to output depending upon the select line, the value of input D after the first, after second, or after third. Okay, fine. So the module provided to us is TFF underscore 8. Code is already given to us, and multiplexer code is not provided to us, that we need to create it. So first of all, let us create a multiplexer code. So create a 4 to 1 multiplexer code. Okay, so give me 1 second. Yes, so first let's write down this multiplexer code. So let me write down this multiplexer code first. So module mux underscore 4 underscore 1, or are they specifying to write down a particular name to it? No, they haven't asked us to use a specific name. Okay, so mux underscore 4 underscore 1. We can also use it inside the always block, the selection logic which we can use, but Okay, I will show you the two ways which we can use it. So first of all, I'm declaring the multiplexer input. Let's say I0, I1, I2, I3, I0, I1, I2, I3, and select lines, input 1 down to 0, select, and output rich. And let me write it down inside an always block. Begin case of select. So if it is 0, 0, then y is equal to I0, and if it is 0, 1, then y is equal to I1, and if it is 1, 0, then y is equal to I2, and if it is 1, 1, then y is equal to I3, and by default y is equal to 0, and in the case and n module. So this is the multiplexer code which I have written. I'm showing you the approach number one, like writing the multiplexer and instantiating and doing. And here I'm going to first of all instantiate my underscore dff, my underscore dff8, let's say dut1, and let me copy this. Yes. So okay, and here the input is 8 bits. We have 3 flip-flops, but the input which we were providing is 8 bits. Previously, the input was only 1 bit. Now it will be 8 bits. Okay, and clock is basically 1 bit only. And we should also have wires. These are also of 8 bits width. So let me declare the wires of 8 bits width. Wire 7 down to 0, W1 and W2. These are the wires which I'm going to have. And yeah. So first let's have the clock connected, next the input D connected, and the output is given to the wire W1. Okay, so output is given to the wire W1, and similarly we have clock W1 and W2. That means the input is W1 and the output is W2. And the last flip flop, so we need to have basically 3 wires because the last flip flop output is also given to the multiplexer. Right? So I'm going to give you one more wire W3 clock. Okay, we have reset also. No, we don't have reset. Clock W2 and W3. Okay, so we have got all this. Now let me instantiate this multiplexer. So let me instantiate mux underscore 4 underscore 1 DUT, it's DUT3 or DUT4. It's DUT3 to 1. And here multiplexer uh, is having the inputs I0, I1, I2 and I3, and you can see this multiplexer is connected with the inputs of 8 bits width. So here also in the design I need to connect with them with 8 bits width, 7 down to 0. Now so I'm going to have I0, sorry, not I0, I'm going to give first input D is connected to 0. So I'm going to write down D and W1, W2 and W3. Okay. So all the outputs of the flip-flops are connected to the multiplexer, right? And select line. So select line is an external input which is already present in the top model, which I'm going to give. And the output of the multiplexer is connected to the output queue here. Okay. Let's run this and let's check it out whether it is working. 213 mismatches. Okay, fine. Okay, fine. Here output should be of 8 bits width that we have missed. Output rich 7 down to 0. Why? Because your output is 8 bits width. Multiplexer output is 8 bits that we have missed it. Let me run it again. Yes, success. So this is how we are going to write it. So just read the statement carefully, and if the statement is not clear, just look into the block diagram, then most of the things will be clear.